Okay, so hi everybody. My name is Pierre Bichon, and so I'm a PhD student working at the MSME lab, so in Créteil, in the south of Paris. So as Jürgen just said, I'm going to talk about contact modeling using the third medium contact method with an application to the femoral stem insertion inside the bone cavity, which is actually an application of the total hip prosthesis surgery. So just to give the context, for this kind of surgery, so it's one of the most common surgery in the world, as you may know. However, there is still quite a high revision rate, with notably more than 10% of the patients that require a revision 10 years after their first surgery. And it has been observed that most of these revisions are due to what we call a bad primary stability, so a bad mechanical fixation of the implant into the bone cavity, which is achieved during the surgery. So what it means is that if we want to reduce the revision rate of this surgery, we need to better assess the primary stability. And so for that, we need to go through simulation. The thing is that for this simulation, we will have to process a contact. And processing a contact, it's something which is known to be not trivial in mechanics for several reasons. So the first reason is that, The first reason is that the contact boundary conditions are always formulated as inequality constraints. The second main difficulty is that for solving this kind of problem, we need to implement algorithms for closest point contact, closest point research, which are algorithms that are known to be very expensive. And so another method has been proposed by Rigors in 2013. So that's basically the third medium contact method. So this method basically consists in considering a third medium between the two bodies that are coming into contact, and then we add an hyperelastic energy to this third medium. And the idea, this is the formulation of the energy. And so this formulation has two main properties. So the first property is that it ensures the non-penetration condition, because when the two bodies are coming into contact, we will have a highly compressed element in the third medium, and so we will have G that will go to 0, and so the energy will go to infinity. At the same time, the negligibility of the effect of this energy on the solution is also ensured by a very small factor gamma that we position in front of the midterm. So that was the first formulation proposed in 2013, but at this moment the method wasn't directly usable because when elements are highly compressed, it could lead to distorted elements that could then lead to differentiation issue. And so several regularization has been proposed to overcome this differentiation issue. So here are two of these regularization, but the thing is that all this regularization was depending on the gradient of the deformation gradient. And so basically it calls the second gradient of U. And it means that if we want to make this regularization useful, then we need to work with P2 element. So to bypass these difficulties, another regularization has been proposed. So the idea is to switch to a mixed variable problem. And so here, Rigors introduced the current formulation for the contact for the third contact method, third medium contact method. Sorry. So that was for the presentation of the method. And so the major assets of these methods are that firstly, we don't need to implement any research closest point research algorithm. The energy is completely differentiable. We don't need to deal with any inequality constraint, and the non-penetration is guaranteed naturally. So now let me go back to my initial problem of an insertion of a femoral stem inside a bone cavity. So here is the femoral stem and here is the bone. So this is a geometry I'm working on. So that's basically a 2D axisymmetric system. And so for the first result, I'm working in a quasi-static regime and without friction. So regarding the boundary condition, I consider the axis of symmetry on the left. I have a prescribed displacement on top, and the displacement is clamped at the bottom. And for the solving method, we simply retrieve the energy, and we sum the energy of each body. We sum, and we solve by differentiating using the UFL differentiation, and we solve using the nonlinear solver of FEniCS. So now let me introduce you my results. So here, what I've done is a parametric sweep on the prescribed displacement on top of the implant. Then I repeat this operation for several values of gamma. So the factor positioned in front of the main term of the formulation of the third medium contact methods. Then I retrieved my contact force, and I compared my result with a previous study that I performed using the Nitsche method, which is a classical approach, a more classical approach for contact processing. And so here what we observe is that more gamma is becoming smaller and more the curves are becoming closer to the Nitsche curves, which is a good point. And so, okay, so here start my contribution. So because our objective was to switch my previous problem into dynamic. So, but the thing is that it's something that hasn't been done yet using the third medium contact method. So far I'm still working on a simplified geometry. So here is my new system so far. So we are still working with a 3-body system, but this time we are working in 2D. And I changed a bit my boundary conditions. So on the two sides, we've got a blocked horizontal displacement. We still have a clamped displacement at the bottom, but we changed a bit the condition on top because here we don't have any prescribed displacement anymore, and we changed it for initial velocity on the whole body. So now let's talk about the theory. So basically what we've done is that if we consider if we consider that our problem, that R is a residual of our problem in quasi-static, then we simply add two mass terms related to the two real bodies to our formulation, and we solve this equation. So before to solve, we discretize using the new mass scheme, and then we solve using the nonlinear solver of FEniCS. So now let me introduce my results. So I compared my results with a 1D study, with the analytical solution of a 1D study. So on the left side, we can observe the displacement actually of the point X, which is just here. And so we can see that this method works pretty well for the displacement because the two curves are matching quite well. However, for the scheme in the middle, so it corresponds to the contact pressure. And we observe that in terms of shape, the curves are okay. However, we can't neglect the fact that there are lots of oscillation. I have to say that the fact to have this oscillation is not something that we couldn't expect, because it's also a problem that we have to face when we are working with a classical approach for contact processing in a dynamic case. And so in order to reduce this oscillation, we use the classical method, which is the modification of the mass matrix. So basically, it consists in removing the density on the nodes of the mass matrix that are related to the contact interface, and to redistribute this density in the rest of the bodies. And so we observe that the curve match better. So just to conclude briefly, so I've presented the third medium contact method, which is not from me, of course. Then I compared the result I've obtained using this method with others that I've obtained using a classical approach, and I proposed an extension of the method to the dynamic regime. Now, for the rest of the work, I still need to consider a more realistic geometry. Then I will need to incorporate friction, and I will need to do model reduction afterward. So, thank you for your attention.
Thank you. So, thank you for a super interesting talk. Are there any questions from the audience?
Yeah, I think it's also super interesting, and I think I will show a bit similar approaches this afternoon. But maybe again, I will ask the same question because we initially had like so maybe I should have said like a body-fitted mesh, right? This is what you're doing.
Sorry, what?
You're tracking the interfaces with the mesh.
So here, with this method, we don't need to track the interface. That's one of the advantages of this method, actually.
Okay, maybe I misunderstood. So you're not tracking the interface?
No.
Ah, okay.
No, because we don't need to retrieve the contact pressure, because the contact pressure is not, I don't know, part of the solution anymore.
Okay. But you said you had, if you have large sort of deformations, you may get distorted elements in cells in the third medium. So it sounds like you're tracking the bodies, the surfaces of the bodies with the mesh.
Sorry, can you repeat? I'm not sure to have understand, but it's because...
Are you moving the mesh nodes of the bodies that are contacting?
Yes, but there are always other nodes that correspond to the third medium mesh in between. And so it means that we don't need to track from one boundary contact, we don't need to track the nodes of the other boundary contact.
Yes.
Okay, so I started to the question.
You're moving the meshes, you're moving sort of the mesh points of the surfaces of the bodies, right?
Yes.
And then you can get distortions. But my question was in a similar way to before. Have you considered like where you don't have a body fitted, let's say you have a fixed mesh from the beginning, just like a cube of the whole domain, and then your bodies are just like fields that are convected.
Eulerian approach.
Sorry.
An Eulerian. So that you don't have to move the mesh node, so you don't get distorted elements or cells. Have you considered that?
No.
Like an Eulerian approach of your...
No.
So I think I will show maybe we can just sort of show different
sure.
results and if it's interesting. So maybe we can get back to that. Yeah.
Okay.
Okay, yeah, Paul first.
I have a question on the friction. How are you planning to incorporate that into the...
So
you already have looked into that?
so far that's something which is still dark for me. But there are some papers that propose to include plasticity in the model, and so it could be right way to incorporate friction.
So I have a question for you.
Yeah.
So I've also tried to use this method, and I tried to do it in 3D.
Okay.
Have you tried to use it in 3D?
Not yet. That's planned. But I know that there is a paper from Riggers, I think, that proposed to implement this method in 3D. So that's basically an extension of the previous formulation. So this one.
Yeah. So what I've seen with this is that the number of iterations you need is crazy. You need like thousands of iterations in your Newton scheme, and you need a partial loading scheme. It might be better when you do time-dependent elastodynamics, but I've really struggled to get this to converge to what they have in their papers, even if the method looks super promising and would solve a lot of things. I would also be interested to see the iteration counts in 2D, because I've also seen that they're quite high for SNES, when you run SNES on this problem, especially with hyperelastic material, it really struggles. So I would be interested to just see the numerics from your side.
Okay.
Because I spent a weekend trying to do this and failed, kind of.
Okay.
Are there any other questions from the audience? Yes?
Just a quick question, since this slide is up, I'd like to understand why you chose this type of regularization.
Why I chose?
This type of regularization.
So that's not my work. And so this was the first one because, sorry, the one on top was the first regularization, and I guess the differentiation problem was due to the deformation gradient, and so we needed to and so we needed to regularize this term, of course. And then the second regularization is because it's easier to work with. Sorry, I should. So here we regularize on the 3-order tensor, and so here we regularize on the two-order tensor, and so that's something better. I hope it answers your question.
So yeah, let's thank the speaker again.
Thank you.